think from this slide onward, that is. Yeah, so the remaining a few slides is to get back to our vibration systems, and in particular here is kind of our first taste of how to formulate the equation of motions. Okay, so for this one, the concept in this way is this: if we have a single degree of freedoms and vibration system such like this, we have mass and damper and spring. And assuming we assign the degree of freedom x and on the translation of the mass block, here kind of give you a notation. Sometimes people like to make a reference for the movement of x, and they either take the middle line of the mass block, or either sometimes some people like to align like a reference to the left side or the right side. My own preference is kind of drawing, just for the drawing purposes, I like to align to the right side, okay, just kind of give you notation. Really, the location of this kind of reference line is not that important. It just indicates that the degree of freedom, okay. So now we have a degree of freedom something like this. So this one, in general, this one would also substitute the external loading F. F is externally applied loading. Usually this function will be given explicitly. Okay. So under these situations, we will be able to formulate the equation of motion. And again, starting from his equilibrium positions, here we assume the mass block be displaced to here. So this is a displacement. Okay. And under that situation, spring is being stretched. So it's going to have the recovering force put it back. And again, assuming we have a velocity, again, going to that direction, so due to damping, and we have the viscous force going to repelling such a motion, so always the damping force or viscous force is to oppose the motion, is to oppose the velocity, okay, increasing in the velocity, so that is in this direction. And so for this case, also this mass have the external force applied. So under the situations, this is the total, the force, I would say the application of the force onto the mass block, and using Newton's second law, and that is due to the force for whatever number of the force we have, 0 to n, will be equal to m times x double dot, using Newton's second law. So basically this whole thing will be equal to this. Okay, so that means the summation of the force, from here you can see by looking at this one, we have f of t. This is first one. Again, that is a sign convention. If we take the sign convention positive, okay, this sign is to follow define the degree of freedom. So, and also the two forces is on the opposite side, so that is minus, let me write it up here, okay? So this force term will be f of t, and minus cx dot, because this force is opposite to the sign convention, and then the same thing for kx. So that is the total forces applied to this mass block. Using Newton's law, mx double dot, x is the point to that direction, okay? So in this way, we rearrange the whole thing, that is mx double dot plus cx dot plus kx, and then leaving this one here, and that is f of t. So from this one, this is the complete description of the equation of motions, okay? And starting from chapter 2, we'll be very rigorously exercise quite a bit examples for formulations, and also for solving this kind of equations. So this is our equation of motion for vibration system under force excitation. And this, if f of t is real non-zero term, then that will be the topic of chapter 3. If f of t is 0, no external loading, then that will be the topic of our chapter 2. Okay, so anyhow, in terms of the mathematical description, M, C, K are constant. So basically this is a linear. And this is the differential equations and ordinary differential equations. Okay? And this one, if Ft exists, if Ft is non-zero, basically that is a forcing term. In terms of the mass, that's called a non-homogeneous term. So entire this is called a non-homogeneous. Linear differential equations. Okay, so most of our exercise will be dedicated to the solution first. So that means solving these equations, and then the remaining will be try to help ourselves how to interpret in terms of the x, how to interpret the result in terms of the respect to our given the physical systems here. So chapter 2 will be for f of t equal to 0, and chapter 3 will be f of t equal to the simple harmonic motion. Sine, cosine will combine, and chapter 4 will be f of t of arbitrary equations. Okay, that means the arbitrary functions, and that one, hopefully everyone can be there, be so strong. Because most of the time that will be in October, and then hopefully I won't, but my experience is people to that moment will become a bit fatigued. Okay, so I will begin to push you. In particular, timing is going to deal with some kind of the, I would say, ugly function. The function is not too easily deal with in terms of the solutions. Okay, and we're going to have a lot of the mathematical tools be introduced at that moment. Okay, so kind of give you a head up. Once we've done this one, then we're happy to move on to multiple degree rhythms. So that means that you will see the more than one math blocks, and that'll be another funny topic. And that moment will be 1 or 2 weeks before the Thanksgiving. I wish this year you have a good Thanksgiving. I wish. Okay, so not threatening you. Okay, so that is the whole pictures here. And another category of example, we will exercise not only translational vibration, but rotational or torsional vibrations. But in terms of the mathematics, and they are the same in the same second order differential equations, linear. Okay, but simply in terms of the modeling, we have a different form. So we're going to discuss this one as well. Okay. So that is the introducing of the harmonic motion. So this is a very simple one. So for this case, you can see equation of motion is mx double dot plus kx equal to 0, or x double dot equal to minus k divided by mx. You can see this term is a constant. So this is simple harmonic motion. Okay. So that is the way. And for this case in particular, if put into our definition last time, this is minus omega n squared. So here we define our natural frequencies. If you still remember, that definition is k over m. And again, in the next chapters, we will formally introduce this notation. But at this moment, if by any chance, any homework you're going to be asked by natural frequencies, you simply plug in this equation first. Okay. So later on, I will give you the formal information. And I think that is pretty much is. We have, okay. How much time do we have? 29, okay. Maybe we can exercise this one, and let me turn off and write the problem statement there, because So this will be our last slide in this chapter. Once we've done this, we're done for today. So we're going to asking is the capital X cosine omega t plus capital X cosine omega plus delta t. So we're going to add this one. This is a little bit different. And the first one, before we do any algebra, I want you to get your attention to this. For this is a cosine, the cosine functions of frequency omega. This is a cosine function which has a frequency other than omega plus delta, a little bit larger, a little bit different. And this is what we're going to do is to exercise the summation of the two cosine functions of different frequencies. Up to this point, before we've been exercised today, is we added a sine or cosine of the same frequencies, but this is a little bit different. Okay, so we can try, but the same mathematics is applied. So I'm going to, again, back to the slide earlier, I provide you, on that single slide, I provide you 5 or 6 trigonometry formulas, and one of that one is here. And let me write it up here. Cosine A plus cosine B, and equal to 2 times cosine A plus B divided by 2 times cosine A minus B divided by 2. So for these questions, for these examples, I'm going to apply these equations. So right now we have the 2 cosine functions and of different arguments. So basically apply that equations, and that will be equal to x cosine omega t plus cosine omega plus delta t. Okay, so hopefully you can compare. So basically for this comparison, A equal to omega t and B equal to this one. So we simply plug in. So that will be equal to 2x cosine delta t. 2 cosine omega plus delta over 2t. Okay, so that is a result, and I want to show graphically what is the result looks like. If you have a slide with you, and you don't need to draw this one. So let me say this is x over t. Okay, so I'm going to draw the result here. And from here you can see this is the compositions of actually multiplication of the two different cosine functions of different frequencies. And how to do this one, how to draw this, and the way you can try is this. You start from here. We're kind of doing the onion with layer by layer. We do the information layer by layer. For the first one, this is a cosine function. So cosine function, right now you just listen because I'm going to mess up the drawing and I will give you the final one, okay? But now you just listen. For cosine functions, and this is a frequency of that cosine functions, okay? So this is a frequency. So that is a cosine functions. You see right now I'm drawing is very light because later I'm going to modify. For the cosine, regular cosine function, it starts from here, that's it, value equal to 1, okay? And then this is a frequency. Frequency is such that from here to here, this is 2 pi period equal to 2 pi divided by frequency. For this case, it is omega plus delta over 2, right? So from here, we define the period, and that is related to the frequency. Okay? And so if only have this cosine and with the magnitude equal to 1, then that situation will be like this. But right now, I'm going to modify how, and the magnitude actually is governed by this. This one representing is the magnitude of the information we draw here. And look at the magnitude. The magnitude actually, the magnitude equal to 2x, and also the magnitude is kind of the fluctuating with time, right? Because that is a function here. So in this case, when t equal to 0, the magnitude equal to 2x. Okay? And this delta is a number less than omega plus delta over 2. So that means when, for example, when t equal to, say, let me draw this one here. So that one equal to this again. This is a cosine function, and why this frequency is lower than this one? Because I realize this is a frequency here. This frequency is less than this one here. So in my drawing, I intend to draw that kind of more relaxed. Okay, so from here to here, that is peak to peak. This is a period equal to 2 pi divided by frequency delta over 2. This is our time scale we put here. Right? Okay, so right now you can see every time, at every time moment, this representing this 2x here. At every time moment, for example, at this time we have this magnitude here, at this time we have this magnitude here. Again, the blue information is an envelope of the vibration of these cosine functions. Okay? So now what I want to do, if I can copy and paste, I simply copy and paste of this blue line to here. So let me do that one here. And now I can precisely join the vibration of this original system. I'm going to use the beta graph of mine. Okay, this is black. So I put this is symmetric. That's an envelope. So for this envelope, the whole vibration basically is confined in such an envelope. Something like this one. Good? Okay. If you have a slice that exactly is shown on this one, so that means in this way the vibrations, the signal of this one basically is confined in the envelope defined by this. And for this one, basically you can see if this amplitude, say if this frequency is such that it is in our hearing range, then basically you can hear it's kind of the beating phenomenon. The beating phenomenon, that means due to certain frequencies, you can see some kind of the beating. Beating, that means some kind of magnitude of the sound is something like this one. Okay, so from here in this way, you can see actually this pattern is basically it's something like this one. The precise drawing will be like this. So basically the pattern of if this frequency is just falling into our hearing range, then you can hear is kind of the pattern of the sound. And for the people call this phenomenon is called the beating phenomena. And the beating frequency basically representing is the patterns of such, I would say, oval shape. The frequency of such an oval shape appearing. So basically the beating frequency is defined by, so this is called the beating period. 1 beat and 2 beats and 3 beats. If you want to define from the 0 to 0, or you want to define from the peak to peak, that is a beating period. You good? Okay, so that is the one. And then later we would have another more discussion on the beating, but now for some reason textbook just kind of show up this one, so I kind of introduced this one earlier here. So by this point, we pretty much finished all the information will be necessary, and one tiny options would be harmonic analysis, and this one I'm going to skip this portion. For the harmonic analysis, and that one involving a Fourier series transform or Fourier series expansion. That one I decided not to be bothered at this moment, but down to the chapter 4, we will wind back to here. Okay. So I think all the information should be enough for you to complete homework 1. And again, the homework 1 is being extended to the end of the day tomorrow. Okay? Yeah, good.